A database is just what the name implies, a base collection of data. The data is organized in some manner so that the information contained within the database can be easily retrieved. Some of the simple databases that you might be familiar with are things like phone books or Rolodexes. As data processing has become more sophisticated, so have methods for collecting, storing, and retrieving information. Databases have become the cornerstone for an overwhelming amount of the computing environment in existence. A database has the following properties. It is a representation of some aspect of the real world or a collection of data elements representing real-world information. A database is logical, coherent, and internally consistent. A database is designed, built, and populated with data for a specific purpose. Each data item is stored in a field. A combination of fields makes up a table. For example, each field in an employee table contains data about an individual employee. A database management system, or DBMS, is a collection of programs that enables users to create and maintain databases and control all access to them. The primary goal of a DBMS is to provide an environment that is both convenient and efficient for users to retrieve and store information. Managing information means taking care of it so that it works for us and is useful for the tasks we perform. By using a DBMS, the information we collect and add to its database is no longer subject to accidental disorganization. It becomes more accessible and integrated with the rest of our work. Managing information using a database allows us to become strategic users of the data we have. We often need to access and resort data for various uses. These may include creating mailing lists, writing management reports, generating lists of selected news stories, identifying various client needs. The processing power of a database allows it to manipulate the data it houses, so it can sort, match, link, aggregate, skip fields, calculate, or arrange. Because of the versatility of databases, we find them powering all sorts of projects. A database can be linked to a website that is capturing registered users, a client tracking application for social service organizations, a medical record system for a healthcare facility, your personal address book in your email client, a collection of word processed documents, or a system that issues airline reservations. There are a number of characteristics that distinguish the database approach from the file-based system or approach. This chapter describes the benefits and features of the database system. A database system is referred to as self-describing because it not only contains the database itself, but also metadata, which defines and describes the data and relationships between tables in the database. This information is used by the DBMS software or database users if needed. This separation of data and information about the data makes a database system totally different from the traditional file-based system in which the data definition is part of the application programs. In the file-based system, the structure of the data files is defined in the application programs, so if a user wants to change the structure of a file, all the programs that access that file might need to be changed as well. On the other hand, in the database approach, the data structure is stored in the system catalog and not in the programs. Therefore, one change is all that is needed to change the structure of a file. This insulation between the programs and data is called program data independence. A database supports multiple views of data. A view is a subset of the database, which is defined and dedicated for particular users of the system. Multiple users in the system might have different views of the system. Each view might contain only the data of interest to a user or a group of users. Current database systems are designed for multiple users. That is, they allow many users to access the same database at the same time. This access is achieved through features called concurrency control strategies. These strategies ensure that the data accessed are always correct and that data integrity is maintained. The design of modern multi-user database systems is a great improvement from those in the past, which restricted usage to one person at a time. In the database approach, ideally each data item is stored in only one place in the database. In some cases, data redundancy still exists to improve system performance, but such redundancy is controlled by application programming and kept to minimum by introducing as little redundancy as possible when designing the database. The integration of all the data for organization within a database system has many advantages. First, it allows for data sharing among employees and others who have access to the system. Second, it gives users the ability to generate more information from a given amount of data than would be possible without the integration. Database management systems must provide the ability to define and enforce certain constraints to ensure that users enter valid information and maintain data integrity. A database constraint is a restriction or rule that dictates what can be entered or edited in a table, such as a postal code using a certain format or adding a valid city in the city field. There are many types of database constraints. Data type, for example, determines the sort of data permitted in a field. For example, numbers only. Data uniqueness, such as the primary key, ensures that no duplicates are entered. Constraints can be simple, like field-based, or complex, like programming. Not all users of a database system will have the same accessing privileges. For example, one user might have read-only access, that is, the ability to read a file but not make changes, while another might have read and write privileges, which is the ability to both read and modify a file. For this reason, a database management system should provide a security subsystem to create and control different types of user accounts and restrict unauthorized access. Another advantage of a database management system is how it allows for data independence. In other words, the system data descriptions or data describing data, metadata, are separated from the application programs. This is possible because changes to the data structure are handled by the database management system and are not embedded in the program itself. A database management system must include concurrency control subsystems. This feature ensures that data remains consistent and valid during transaction processing, even if several users update the same information. By its very nature, a DBMS permits many users to have access to its database, either individually or simultaneously. It is not important for users to be aware of how and where the data they access is stored. Backup and recovery are methods that allow you to protect your data from loss. The database system provides a separate process from that of a network backup for backing up and recovering data. If a hard drive fails and the database stored on the hard drive is not accessible, the only way to recover the database is from a backup. If a computer system fails in the middle of a complex update process, the recovery subsystem is responsible for making sure that the database is restored to its original state. These are two more benefits of a database management system. The so-called semantic modeling method nowadays is commonly used in database structure design. Semantic modeling is modeling data structures based on the meaning of these data. Different variants of the entity relationship diagrams are used as a tool for the semantic modeling. ER model-based diagrams have three main components: an entity, a relation, and attributes. An entity is a class of similar objects, information about which should be taken into account in the model. Each entity must have a name, expressed by a noun in the singular. Examples of entities can be such classes of objects as supplier, employee, or invoice. Each entity in the model is depicted in the form of a rectangle with the name. While determining the type of entity, it is necessary to be sure that each instance of an entity may be indistinguishable from any other instance of the same entity. Relation is presented in the form of a non-directional line connecting two entities or leading from the entity to itself. In the place of docking, an entity uses 3-point entry to the entity rectangle, if many instances of the entity may be used for this relation. Single-point entry if relation can or should participate in only one instance of the entity. Relation between entities ticket and passenger connects passengers and tickets. One side of the relation with a label for is a many-to-many relation, which allows to relate more than one ticket to a passenger, and each ticket must be linked to any passenger. Another side of the relation with a label have is a 0 or 1 relation, which shows that each ticket can belong to only one passenger, and the passenger is not obliged to have at least one ticket. Attribute of an entity is a detail or feature that is used for verification, identification, classification, numerical characteristics, or expressing status of the entity. Attribute names are recorded in the rectangle representing an entity under entity name. For instance, an entity human being may have such attributes as gender, year of birth, first name, etc. The relational data model was introduced by C.F. Codd in 1970. Currently, it is the most widely used data model. The relational model has provided the basis for research on the theory of data, relationship, constraint, numerous database design methodologies, the standard database access language called Structured Query Language or SQL, and almost all modern commercial database management systems. Furthermore, the relational data model describes the world as a collection of interrelated relations or tables. Now let's talk about the fundamental concepts in the relational data model. A relation, also known as a table or file, is a subset of the Cartesian product of a list of domains characterized by a name, and within a table, each row represents a group of related data values. A row or record is also known as a tuple. The columns in a table is a field and is also referred to as an attribute. You can also think of it this way. An attribute is used to define the record, and a record contains a set of attributes. The steps I'm about to mention outline the logic between a relation and its domains. Given n domains are denoted by d1, d2, up until dn, and R is a relation defined on these domains, then R has some or all elements of d1, x d2, x up until xdn. Now let's talk about tables. A database is composed of multiple tables, and each table holds the data. And then we talk about columns. A database stores pieces of information or facts in an organized way. Understanding how to use and get the most out of databases requires us to understand that method of organization. The principal storage units are called columns or fields or attributes. These house the basic components of data into which your content can be broken down. When deciding which fields to create, you need to think generically about your information. For example, drawing out the common components of the information that you will store in the database and avoiding the specifics that distinguish one item from another. And then we move to domains. A domain is the original set of atomic values used to model data. By atomic value, we mean that each value in the domain is indivisible as far as the relational model is concerned. For example, the domain of marital status has a set of possibilities: married, single, divorced. The domain of shift has the set of all possible days: Monday, Tuesday, Wednesday, etc. The domain of salary is the set of all floating point numbers greater than 0 and less than 200,000. The domain of first name is the set of character strings that represents names of people. In summary, a domain is a set of acceptable values that a column is allowed to contain. This is based on various properties and the data type for the column. We will discuss data types in another chapter. And now we move to records. Just as the content of any one document or item needs to be broken down into its constituent bits of data for storage in the fields, the link between them also needs to be available so that they can be reconstituted into their whole form. Records allow us to do this. Records contain fields that are related, such as a customer or an employee. As noted earlier, a tuple is another term used for record. Fields can hold a range of different sorts of data. This one has a record ID field. This is an ordinal number. Its data type is an integer. A pubdate field. This is displayed as day/month/year. Its data type is date. An author field. This is displayed as initial, surname. Its data type is text. And a title field text. Free text can be entered here. You can command the database to sift through its data and organize it in a particular way. For example, you can request that a selection of records be limited by date. That is, number 1, all before a given date. Number 2, all after a given date. Or number 3, all between two given dates. Similarly, you can choose to have records sorted by date. Because the field or record containing the data is set up as a date field, the database reads the information in the date field not just as numbers separated by slashes, but rather as dates that must be ordered according to a calendar system. Degree. The degree is the number of attributes in a table. Okay, now let's talk about the properties of a table. A table has a name that is distinct from all other tables in the database. There are no duplicate rows. Each row is distinct. Entries in columns are atomic. The table does not contain repeating groups or multi-valued attributes. Entries from columns are from the same domain based on their data type, including number, like numeric, integer, float, or small integer, character, string, date, logical, like true or false. Operations combining different data types are disallowed. Each attribute has a distinct name, and the sequence of columns is insignificant. The sequence of rows as well is insignificant. Now let's talk about the types of data models. High-level conceptual data models. High-level conceptual data models provide concepts for presenting data in ways that are close to the way people perceive data. A typical example is the entity relationship model, which uses main concepts like entities, attributes, and relationships. An entity represents a real-world object such as an employee or a project. The entity has attributes that represent properties such as an employee's name, address, and birth date. A relationship represents an association among entities. For example, an employee works on many projects. A relationship exists between the employee and each project. Record-based logical data models. Record-based logical data models provide concepts users can understand but are not too far away from the way data is stored in the computer. 3 well-known data models of this type are relational data models, network data models, and hierarchical data models. The relational model represents data as relations or tables. For example, in the membership system at Science World, each membership has many members. The membership identifier, expiry date, and address information are fields in the membership. The members are individuals such as Mickey, Minnie, Mighty, Door, Tom, King, Man, and Moose. Each record is said to be an instance of the membership table. The network model represents data as record types. This model also represents a limited type of one-to-many relationship called a set type. Data modeling is the first step in the process of database design. This step is sometimes considered to be a high-level and abstract design phase, also referred to as conceptual design. The aim of this phase is to describe the data contained in the database, example, entities like students, lecturers, courses, subjects. The relationships between data items, example, students are supervised by lecturers, lecturers teach courses. The constraints on data, example, student number has exactly 8 digits. A subject has 4 or 6 units of credit only. In the second step, the data items, the relationships, and the constraints are all expressed using the concepts provided by the high-level data model. Because these concepts do not include the implementation details, the result of the data modeling process is a semi-formal representation of the database structure. This result is quite easy to understand, so it is used as a reference to make sure that all the user's requirements are met. The third step is database design. During this step, we might have two sub-steps, one called database logical design, which defines a database in a data model of a specific DBMS, and another called database physical design, which defines the internal database storage structure, file organization, or indexing techniques. These two sub-steps are database implementation and operations/user interfaces building steps. In the database design phases, data are represented using a certain data model. The data model is a collection of concepts or notations for describing data, data relationships, data semantics, and data constraints. Most data models also include a set of basic operations for manipulating data in the database. In this section, we will look at the database design process in terms of specificity. Just as any design starts at a high level and proceeds to an ever-increasing level of detail, so does database design. For example, when building a home, you start with how many bedrooms and bathrooms the home will have, whether it will be on one level or multiple levels, etc. The next step is to get an architect to design the home from a more structured perspective. This level gets more detailed with respect to actual room sizes, how the home will be wired, where the plumbing fixtures will be placed, etc. The last step is to hire a contractor to build the home. That's looking at the design from a high level of abstraction to an increasing level of detail. The database design is very much like that. It starts with users identifying the business rules, then the database designers and analysts create the database design, and then the database administrator implements the design using a DBMS. The following subsections summarize the models in order of decreasing level of abstraction. External models represent the user's view of the database and contain multiple different external views that are closely related to the real world as perceived by each user. Conceptual models provide flexible data structuring capabilities and present a community view. The logical structure of the entire database contain data stored in the database show relationships among data including constraints, semantic information such as business rules, security, and integrity information. Consider a database as a collection of entities or objects of various kinds that are the basis for identification and high-level description of main data objects. They avoid details which are database independent regardless of the database you will be using. And now let's talk about internal models. The three best-known models of this kind are the relational data model, the network data model, and the hierarchical data model. These internal models consider a database as a collection of fixed-size records that are closer to the physical level or file structure, a representation of the database as seen by the DBMS. It also requires the designer to match the conceptual model's characteristics and constraints to those of the selected implementation model. It also involves mapping the entities in the conceptual model to the tables in the relational model. Physical models are the physical representation of the database, and they have the lowest level of abstractions and are how the data is stored. They also deal with runtime performance, storage utilization and compression, file organization, and access methods. Data encryption are the physical level, managed by the operating system or OS. It also provides concepts that describe the details of how data are stored in the computer's memory. Data abstraction layer. In a pictorial view, you can see how the different models work together. Let's look at this from the highest level, the external model. The external model is the end user's view of the data. Typically, a database is an enterprise system that serves the needs of multiple departments. However, one department is not interested in seeing other departments' data. Example, the human resources or HR department does not care to view the sales department's data. Therefore, one user view will differ from another. The external model requires that the designer subdivide a set of requirements and constraints into functional modules that can be examined within the framework of their external models. Example, human resources versus sales. As a data designer, you need to understand all the data so that you can build an enterprise-wide database. Based on the needs of various departments, the conceptual model is the first model created. At this stage, the conceptual model is independent of both software and hardware. It does not depend on the DBMS software used to implement the model. It does not depend on the hardware used in the implementation of the model. Changes in either hardware or DBMS software have no effect on the database design at the conceptual level. Once a DBMS is selected, you can then implement it. This is the internal model. Here, you create all the tables, constraints, keys, rules, etc. This is often referred to as the logical design. The physical model is simply the way the data is stored on the disk. Each database vendor has its own way of storing the data. Now let's talk about schemas. A schema is an overall description of a database, and it is usually represented by the Entity Relationship Diagram, or ERD. There are many subschemas that represent external models, and thus display external views of the data. Following are a list of items to consider during the design process of a database. Let's talk about external schemas. First, you have your multiple subschemas. These display multiple external views of the data. Then you have your conceptual schema. There is only one. This schema includes data items, relationships, and constraints, all represented in an ERD. Then you have your physical schema. There is only one. Logical and physical data independence. Data independence refers to the immunity of user applications to changes made in the definition and organization of data. Data abstractions expose only those items that are important or pertinent to the user. Complexity is hidden from the database user. Data independence and operation independence together form the feature of data abstraction. There are two types of data independence, logical and physical. Let's first talk about logical data independence. A logical schema is a conceptual design of the database done on paper or a whiteboard, much like architectural drawings for a house. The ability to change the logical schema without changing the external schema or user view is called logical data independence. For example, the addition or removal of new entities, attributes, or relationships to this conceptual schema should be possible without having to change existing external schemas or rewrite existing application programs. In other words, changes to the logical schema, example, alterations to the structure of the database like adding a column or other tables, should not affect the function of the application, like external views. Physical data independence refers to the immunity of the internal model to changes in the physical model. The logical schema stays unchanged even though changes are made to file organization or storage structures, storage devices, or indexing strategy. Physical data independence deals with hiding the details of the storage structure from user applications. The applications should not be involved with these issues since there is no difference in the operation carried out against the data. Relational algebra is procedural query language, which takes relation as input and generate relation as output. Relational algebra mainly provides theoretical foundation for relational databases and SQL. Now let's talk about operators in relational algebra. We'll start with projection, which is represented by the pi sign. Projection is used to project required column data from a relation. Example: R, A, B, C, 1, 2, 4, 2, 2, 3, 3, 2, 3, 4, 3, 4, pi, BC. BC, 2, 4, 2, 3, 3, 4. Note, by default, projection removes duplicate data. Now let's talk about selection, which is represented by the sigma sign. Selection is used to select required tuples of the relations. For the following relation, sigma c greater than 3r will select the tuples which have c more than 3. Note, selection operator only selects the required tuples but does not display them. For displaying, data projection operator is used. For the following selected tuples, to display we need to use projection also. Pi sigma c greater than 3r will show following tuples: A, B, C, 1, 2, 4, 4, 3, 4. Now we move to union, represented by the letter U. Union operation in relational algebra is same as union operation in set theory. Only constraint is for union of two relation, both relation must have same set of attributes. And now for set difference, which is represented by the minus sign. Set difference in relational algebra is same set difference operation as in set theory, with the constraint that both relations should have same set of attributes. Now let's talk about rename, which is represented by the raw sign. Rename is a unary operation used for renaming attributes of a relation. Raw A over BR will rename the attribute B of relation by A. And now for cross product, represented by the letter X. Cross product between two relations, let's say A and B, so cross product between A x B will result all the attributes of A followed by each attribute of B. Each record of A will pair with every record of B. The following is the example. Here you have two sets, A and B, A representing name, age, sex, and B with ID and course. So under name you have Ram, Sana, Kim, age 14, 15, 20, sex, male, female, male. And then you have ID 1 and 2, and course DS and DBMS. When you go AXB, it becomes name, age, sex, ID, course, and you have RAM 14, M, 1, DS, RAM 14, M2, DBMS, Sana 15, F1, DS, Sana 15, F2, DBMS, Kim 20, M1, DS, Kim 20, M2, DBMS. Note, if A has n tuples and B has m tuples, then A x B will have n times m tuples. And now we move to natural join, represented by the bow tie sign. Natural join is a binary operator. Natural join between two or more relations will result in a set of all combinations of tuples where they have equal common attributes. Let's see the following example. Here you have two sets, one EMP signifying employee and another DEP signifying department. Under employee you have name, ID, department name. Under DEP you have department name and manager. Under name you have A, B, C, D, ID 120, 125, 110, 111. Department name, IT, HR, Sale, IT. Under DEP's department name you have Sale, Prod, and IT. And under manager you have YZA. So employee natural join department becomes name, ID, department name, manager with the following details. ACD 120, 110, 111, IT, Sale, IT, AYA. And then you have conditional join. Conditional join works similar to natural join. In natural join, by default, condition is equal between common attribute, while in conditional join, we can specify any condition, such as greater than, less than, not equal. Let's see the following example. You have two sets, R and S. Under R, you have ID, sex, and marks. Same goes with set S. Under ID, you have 1, 2, 3. Under sex, FFF. Under marks, 45, 55, and 60. Under S, ID 10, 11, 12. Sex, MMM. Marks, 20, 22, 59. Join between R and S with condition R marks are greater than or equal to S marks, you will have the following set. RID, R sex, R marks, SID, S sex, S marks. And then you have the following data. Under RID, 1, 1, 2, 2, 3, 3, 3. Under R sex, FFFFFFF. Under R marks, 45, 45, 55, 55, 60, 60, 60. Under SID, 10, 11, 10, 11, 10, 11, 12. Under S sex, you have all MMM. And under S marks, you have 20, 22, 20, 22, 20, 22, 59. Relational algebra received little attention outside of pure mathematics until the publication of E.F. Codd's Relational Model of Data in 1970. Codd proposed such an algebra as a basis for database query languages. 5 primitive operators of Codd's algebra are the selection, the projection, the Cartesian product, also called the cross product or cross join, the set union, and the set difference. And finally, let's talk about set operators. The relational algebra uses set union, set difference, and Cartesian product from set theory, but adds additional constraints to these operators. For set union and set difference, the two relations involved must be union compatible. That is, the two relations must have the same set of attributes. Because set intersection is defined in terms of set union and set difference, the two relations involved in set intersection must also be union compatible. For the Cartesian product to be defined, the two relations involved must have disjoint headers. That is, they must not have a common attribute name. In addition, the Cartesian product is defined differently from the one in set theory, in the sense that tuples are considered to be shallow for the purposes of the operation. That is, the Cartesian product of a set of n tuples with a set of m tuples yields a set of flattened n plus m tuples, whereas basic set theory would have prescribed a set of 2 tuples, each containing an n tuple and an m tuple. More formally, R times S is defined as follows. Display style R \, times S : equals \ R underscore 1, R underscore 2, dots, R underscore n, S underscore 1, S underscore 2, dots, S underscore m, R underscore 1, R underscore 2, dots, R underscore n, \ in R, S underscore 1, S underscore 2, dots, S underscore m, in S, R \, times S : equals r underscore 1, r underscore 2, dots, r underscore n, s underscore 1, s underscore 2, dots, s underscore m, r underscore 1, r underscore 2, dots, r underscore n, in r, s underscore 1, s underscore 2, dots, s underscore m in s. The cardinality of the Cartesian product is the product of the cardinalities of its factors, that is, r times s equals r times s.